welcome. Today we will be talking a little bit about molecules and how molecules form, how are the levels of these kind of quantum systems, and so on and so forth. So in the previous sessions we spoke a little bit about atoms and how we basically went through how the atomic potential is introduced into the Schrödinger equation. And then, although we didn't do every algebraic step, we more or less saw what comes out of solving the Schrödinger equation in the case of the hydrogen atom, which basically involves only the positions and the motion of the proton in the nucleus and the electron that is orbiting around it. And by solving the Schrödinger equation, we basically found that three quantum numbers arise naturally. One is the principal quantum number n, which basically tells us about the amount of energy. So the energy of the system is minus 13.6 electron volts divided by n squared. And n runs from 1 to infinity. And we also had L, which is related to the angular momentum of the electron. So it basically relates to the angular momentum, the orbital angular momentum of the electron in the so-called orbits around the nucleus. Although talking about orbits is not strictly speaking correct anymore, because we're not talking about just particles, but also a particle wave. But in a sense, this L number gives us, intuitively at least, a measure of the amount of angular momentum of the electron orbiting around the nucleus. And we also had another number which is called m, which refers basically to the projection of this angular momentum in the z-axis, which is something a little bit technical and essentially just defines how much of this angular momentum is pointing up or down, and so on and so forth. So with the combinations of all these numbers, we were able to label all the quantum states of the atom. And we also introduced a little bit artificially, because that doesn't come out naturally from solving the classical Schrödinger equation, the spin, which is another more intrinsic property of the electron, which can have two possible states, so plus 1/2 or minus 1/2, and it's essentially with these four numbers we have a full picture of all the levels that atoms can have, and well, in particular the hydrogen atom. But other atoms more or less follow the same sort of level structure, although the values might vary a bit. So maybe the minus 13.6 electron volts is no longer exactly right. The labels will still be the same for all atoms. So we still have a principal quantum number and the angular momentum and the projection of the angular momentum and the spin for each electron. And with that, we basically can build the electronic configurations of all the atoms, which is more or less where we stopped last time. So looking at a diagram like this one, where the levels are ordered in certain particular ways, and all these orbitals or all these quantum levels or quantum states are filled in a particular order. All of that we discussed already, and basically what we want to talk about today is what happens when we, for example, bring together two atoms of hydrogen, or two other atoms, to any atoms, or three or four or more. How does this work in terms of having and producing molecules, which we know, you probably know already, they exist. So, okay, let's talk a little bit about that. So, in the case of bringing two hydrogen atoms close together, in principle, if there was no interaction between them, we would have the quantum levels of one and the quantum levels of the other one, which are pretty much identical, and they follow exactly the same rules that we've already studied. But in this case, when we bring them close enough, something interesting happens. Each one of the levels of each one of these two atoms, and let's think at the moment, let's just think on the ground state, and let's just think simple, hydrogen atoms. So if we bring these two hydrogen atoms, what will happen is at some point the electronic wave functions or the probability distributions will start overlapping. And then in that moment, the electrons from one and the other will start interacting with each other, and we'll start seeing the nucleus of the other and so on. And in that moment, the atoms themselves are no longer quantum systems or insulated quantum systems, but the entire system now with two nuclei and two electrons becomes one single quantum system. And something interesting happens. In that case, two things, or each one of the states, let's say the one S state of this atom and the one S state of the other atom, they basically combine, let's say, and form two different states, one with higher and one with lower energy. And these two states are actually known as the bonding and anti-bonding state. And this is what we see here. So let's imagine we can have two quantum, the two atoms over here, and these two atoms could either have two wave functions that are basically in phase with each other, or we can have two wave functions that are in antiphase with each other. So this is something a little bit technical, and we can discuss it in more detail later. But basically, what will happen is when we superimpose these two wave functions, we either get a wave function that looks a bit like that, where most of the probability of finding the electrons will be found in the space between the two nuclei. And the other possibility is that they interfere destructively in the center. They produce a node, so there's zero probability of finding them right in the center between the two nuclei, and they will more or less distribute the electrons far away from each other. So this is depicted in these two pictures down here. So basically they either interact in a way in which the electrons are preferably or mostly in between the two nuclei, or they go to a state in which the electrons are mostly in the outside, also, or on the sides of the two nuclei far away from each other. Okay, so if that is the case, basically let me just make a very simplistic argument around why these two states will have different energies and so on, and why we call them the way we call them, the bonding and the anti-bonding state. Okay, let's think that we have the two positive nuclei, so we brought them together, so they are standing right there. And let's imagine we have the bonding state. So the bonding state is in which the two wave functions interfere constructively in the center. So this means that the most likely region to find electrons, both electrons, will be here in the center. So let's, for simplicity, imagine that we have the two electrons there, more or less. And what we want to now also, just intuitively, let's think of what are the forces on this nucleus, for example. So this nucleus will feel a strong attraction towards the first electron, the electron that is closest to it. So this electron will strongly attract this nucleus just because they are close to each other. So there will be a strong force on the nucleus in that direction. Then there will be also a weaker but still relatively strong force, that is the attraction of this electron to this nucleus. So in that case, we will have one more force that is still small, well, a little bit smaller than the other one, but still in the same direction, attracting the nucleus towards the center of the molecule, let's say. And it will have also a repulsion felt from this positive charge. So these two positive charges will repel each other, but since they are farther apart, this force will actually be very, very small. Okay, so all in all, if we add all these three forces, what we have is a total force that falls in this direction. So it's an attractive force. The entire system, so the rest of the system, let's say, so the two electrons and the other nucleus in total are attracting this nucleus on the right towards the center. And exactly the same happens to the other nucleus. So this other nucleus here will feel a strong attraction from this electron, slightly smaller attraction from this other electron, and a slight, very, very slight repulsion from the other nucleus. So we have something very similar, the two attractions from the electron and a very, very small repulsion from the other nucleus. So in total, this one will feel a force that goes in this direction. And as you see, if this state forms in which the electrons interfere coherently in the center, and they interfere constructively in such a way that they like, let's say, or the probability of finding, they're mostly in between the two nucleus, a force emerges naturally in between the two atoms, between the two nuclei, that brings them together. And that's why we know this or that's why we call this state the bonding state. Okay? Let's see the other case. In the other case, what we obtain is a destructive interference in the center. So let's place again the two nuclei positively charged there. And now, in the anti-bonding state, the two electrons interfere destructively in the region in between the two nuclei, and therefore we will preferably find them somewhere in these regions, here and here. So again, for simplicity, let's just assume that we can find them right there, and let's do the same that we did in the previous case. So if the electrons now are on the sides, these nucleus will feel a strong attraction towards this electron. Then it will feel a repulsion from the other nucleus, which is also there. And it will feel a very, very, very faint attraction towards this electron, which is actually quite far away. So in that case, there will be a very, very weak force in this direction. So all in all, if we add all these forces, what this nucleus will feel is a repulsion towards this in this direction, or a force in this direction. The same happens in the other case. So it will feel a strong attraction in this direction, plus a little bit of repulsion from the other nucleus, plus a tiny, tiny attraction from the electron in the other side. And again, all in all, this nucleus will, or this atom will feel repulsive force, and basically, in this case, it will tend not to form a molecule. In the case of hydrogen, of course, other atoms that have more than one electron each, things get complicated, because maybe some of the electrons will fall in a bonding state, some electrons will fall in an anti-bonding state, and therefore one has to consider which ones are, if the bonding or the anti-bonding states contribute more towards the formation or the dissociation of these molecules. It so happens that then the bonding and anti-bonding states basically are the result of combining the two atomic orbitals, and one of them produces a lower energy state, which is usually the bonding state, and the other one produces a higher energy state, which is the anti-bonding state. And therefore, in many cases, the combination of atoms produces molecules, because the bonding state is more favorable energetically. Okay, if we do all the math, the quantum mechanical math properly, here are all the integrals that come out when you calculate the energy and all the terms that come into the energy of the different states. And as you can see, from the second to the last line, they are all basically terms that involve directly the charge mediated interactions. So all of them involve charges, but this term S only involves the overlap of the two electronic wave functions. So this is actually one the main contribution to differentiate the energy of the two bonding and anti-bonding states, which are shown here. So this sign, as you can see, changes between the energy of one and the other, and essentially this is what makes the difference between the two cases, and what lowers the total energy of the bonding state with respect to the anti-bonding. So one other thing that arises from having more than one atom in a molecule is not just these bonding and anti-bonding states. Other interesting things that don't happen in the individual atoms start happening with molecules. For example, molecules that have 2 or 3 or 4 atoms and so on, they can rotate. So now we will have also energy that can be stored in this rotation of the entire molecule. And this will give additional degrees of freedom. We can also think of the atoms as being bound to each other by little springs. So this force that keeps them together but not too close together essentially behaves a little bit like a spring. So molecules will be able to now vibrate and do other motions that are also very very interesting, like torsional motions or vibrations and combinations of those with rotations as well. So in principle, we can excite all these levels, and although in principle, for example, rotational levels should be equispaced to first approximation, that's not necessarily true, because as the molecule starts rotating, the centripetal force starts also deforming the molecule, and if the molecule deforms, then the potential and all the vectors that are involved in the potential change, and that means that the levels will also change. So when one considers properly all the entire problem, one finds that for example, rotational spectra could be very, very complicated. This is actually an absorption spectrum of water vapor in the atmosphere. And as you can see, there's lots and lots of different absorption peaks. Each one of these absorption peaks is related to the transition of from one to another rotational state of the water molecule. So since water is very dipolar, it interacts very heavily with electromagnetic radiation, and therefore it shows all these bunch of different absorption peaks that you see here in the slide, and all of these are related to the transition between two different rotational states. The same can apply to other molecules, many molecules that are even much more complicated than water, for example. And I'm not going into all these details, but I want now to move on to other forms of materials, not just gases, in which the molecules are further apart and they can rotate and vibrate more or less as if they were independent, insulated quantum systems. But when you have a liquid, the molecules are much closer together, and they start establishing also interactions between them. So all these molecules will now feel certain forces, for example, hydrogen bonds or other weak interactions among them. And this means that they are not as free to rotate and vibrate and have all these motions that they can have in gas form. And in the case of a liquid, the interaction is no longer with a single molecule, but really is with the ensemble of all these molecules that already have built-in interactions between them. So, for example, in the case of liquid water, just going back to the same liquid, well, the same material, but in liquid form, what we will find is that the water, if we make the same sort of experiment and measure the transmission through water in liquid form, instead of having a bunch of discrete peaks that are related to the transition between rotational states, what we have is a continuous soft curve of absorption. That is the one I show here, in which basically what we see is just the interaction of all these bunch of different water molecules that we excite with each other, but they can no longer freely move, and therefore it's more like a damped type of rotation and vibration state. So really in this case the interaction is now with something more complex, because the entire system is the whole liquid. Even a more extreme case, for example, is the case of a crystal. So a crystal is a material that has all these order in their atoms. So the atoms or the molecules or whatever that forms the crystal, for example, a semiconductor or many metals or many other materials also form crystalline lattices. The lattices you can also imagine these lattices as being a bunch of masses attached to the first neighbors by springs. And you can imagine that if you push this lattice, you can produce a coherent vibration of the entire lattice. And these vibrations of the entire lattice are called phonons. And we can also do spectroscopy on these kinds of phonons, and they tend to have a more or less distinctive absorption peak, which it relates, of course, to the particular form of the unit cell, so the basic molecule, but also to the entire lattice. So here in this case, the quantum system is no longer a single atom or a bunch of atoms in a molecule, but more like the entire lattice, and we can excite these vibrational transitions in the systems. More complex molecules, of course, will show more degrees of freedom, so they can have torsions, complicated motions that involve many atoms and the deformation of several of their bonds and so on. And these can make what we call collective vibrations. One very good example is what the proteins are. Proteins are extremely big molecules. Just for you to have an idea, the smallest proteins will have around 10,000 atoms. So they are really super complex molecules, and these molecules have particular three-dimensional shape, and the way they vibrate actually defines many of their biological functions and so on. So understanding the vibration of these kinds of more complex systems, and very particularly not just the vibration of one atom against the other, but more the collective vibrations that involve the motion of the entire molecular structure, are very, very important in understanding what these types of molecules. So, for example, these is the vibrational spectrum, at least in the bottom, that was measured from this molecule that is shown there. And what we observe is that, for example, simulations that can be done, and by simulations is quantum mechanical calculations of how the orbitals, so all the distribution of the electrons in all these atoms, carbons and hydrogens and so on, behave, and how they overlap, and how much force is between all these different atoms, and how we do a full calculation of these molecules done. That's what you see in the top. All these spikes that you see here are the vibrational frequencies that are calculated quantum mechanically, and if you add some width to each one of them, you can obtain this dotted curve that looks here, and that's a prediction of what the absorption should look like And as you can see, it more or less fits well with the experiment, and we can look at particular motions that, for example, this one that is there with a red arrow there is a particular vibrational motion of this molecule, and this is actually the quantum mechanical calculation of how these atoms are expected to vibrate in this molecule. So very, very precise quantum mechanical calculations can be done nowadays for these kinds of systems, even though they are really complicated systems. I mean, you can imagine by just solving the hydrogen atom, we had to deal with a relatively complicated already Schrödinger equation. So including all the electrons and everything in this molecule, for example, will involve hundreds of variables, hundreds of positional variables, and so on. And solving that Hamiltonian is something that is relatively complex. However, these computational programs, what they do is they take the potential of a molecule, and they already have built-in ways of calculating what the potentials look like when you put, for example, together two carbons, or one carbon and one hydrogen, and so on and so forth. So they can have a good estimation of what the potential looks like in a complex molecule, and then they do approximations. They already have a set of eigenfunctions and eigenvalues that resemble very well all these orbitals, and basically they do iterations in order to get the amplitudes and the details and all the parameters that come with all these wave functions to fit that particular Hamiltonian. So essentially, these calculations are actually very precise in many cases, and let us do very, very good estimations of what the spectrum or the behavior or the interactions among these molecules could look like. One other interesting thing is that when you have complicated molecules, you will have the interactions, the vibrations of the molecule, like the one we just saw in the previous slide. But you will now start also establishing intermolecular, interactions. So interactions that go from one molecule to the next. And now also molecules will be able to vibrate against each other or do complicated things. And all these interactions can be accounted for in many ways. So and all of these interactions also give rise to interesting physics that we can study and benefit from. I would like to finish this session on molecules. I hope I gave you at least a feeling of what the way we understand and see molecules from the quantum mechanical point of view looks like. We try to understand how bonds between two molecules form. Of course, all the details can be studied if you're interested. There are lots of different videos. There are very good articles in Wikipedia. There are excellent books and so on. And if you are gonna do, for example, synthesis during your thesis, or you're gonna do more chemical work, or even theoretical work in predicting orbitals or properties of molecules, you're of course encouraged to look into the details more. But I would like to finish the session with this, and thank you very much for taking part.